Good afternoon, dear participants. I welcome you all for today's webinar topic on fundamentals of electromagnetism. We have with us today's resource person, Dr. Mahadeva Prasad. Dr. Mahadeva Prasad has completed his master's degree in physics from University of Mysuru while securing 6th rank. He cleared state-level eligibility test for lectureship conducted by Kuempu University in the year 2006. He was awarded PhD degree from the University of Mysuru in the year 2012 under the guidance of Professor Shashidhar Prasad, former Vice Chancellor of University of Mysuru. He has published 18 research papers both on national and international journals and presented 2 papers at state level conference and 5 papers at national conference and 1 paper in international level workshop. He has experience at premier research institutes of India like IASC and RRI. He worked as research assistant at Raman Research Institute, Bangalore. He completed a course called Introduction to Java Programming at Indian Institute of Science, Bangalore by securing a good grade. He has a teaching experience at various places, like he worked as a faculty in MES College, Malleshwaram, Bangalore, and Yam Vishwesvaraya Institute of Technology, Bangalore, Sadgupta College, Mysuru, Madhumalappa College, Mysuru, Regional Institute of Educational, Mysuru. And currently he is working as Assistant Professor of Physics, Government Postgrad College, Bannur. I immensely welcome Dr. P. Mahadeva Prasad for this webinar. Over to you, sir.
Thank you, madam. So, for welcome. So, good afternoon to all of you, those who are hearing participants. Now, today, let us learn about fundamentals of electromagnetism. We start our journey from physics and move towards the laws which governs the electromagnetism. Let us ask some basic questions. So what is physics? So immediately answer comes. So physics is a study of nature. Again, the question arises, what is nature? The entire material world around us is called nature. Mountains, valleys, rivers, hill stations, etc. All these constitute nature. Who created nature? Nobody has created nature. It existed. It continues to exist. But during the course of time, the nature changes. Now we are living in a time, we are living in an era such that, so we have so much advances in all walks of life. So in science and technology also. Let us list a few achievements, what we have achieved in the field of science and technology. Number 1. So in the field of communication, so one can establish communication from one place of Earth to the other place of Earth within fraction of a second using a mobile phone without having any physical connection, a wire connection between those two. So also in the field of medicine, one can have a 3-dimensional view of the human brain without doing any dissection. So one can determine a small tumors present in a brain using MRI scanning. Also, we have space explorations, rockets. See here, similar to this one, rockets takes satellites to the orbit. We use satellites for many purposes. One is for communication purpose, other is for weather forecasting. Weather forecasting means remote sensing satellites. So we have achieved so many advances in the case of space explorations. So also in the field of engineering, we have constructed multi-story buildings, dams, tunnels, etc. Right? So in the field of transportation, from one place of the earth to the other place of the earth, one can move within 24 hours by using a sort of aeroplane. We have high sophisticated cars we have. So similarly, we have a racer car, fast moving vehicles like bullet trains, etc. Also, there are many ships which carries tons of loads which moves over the seas. Also, we have submarines which moves inside the water also. So the list goes on. The list goes on. We have so much of advances in all fields, all walks of life. Now, the question is, if the time runs back about 1,000 years, 1,000 years back, the same intelligent human beings called Homo sapiens were living on the surface of the earth, right? But 1,000 years back, we did not have all these technologies. Now we have technologies. The question is, how did we achieve all these sophistications, right? How did we achieve all this sophistication? By a method, what we call as scientific method. So what is a scientific method? Observation, reason, and experiment is called scientific method, right? So physics is a experimental science. So physics is based on observation. So among many observations made by Greeks, there were two very important ones. So one observation is a strange rock from the island of Magnesia, which attracted iron, right? So that was deemed to be the beginning of magnetism, right? So the naturally occurring stones or lodestones, which have been magnetized very naturally. See, when Greeks discovered these rare stones, they amused by their property of attracting small bits and pieces of iron over short distances. You can see, I will show you a photograph, you can see here. So you can see small pieces of lodestones where small pieces of iron are clinging towards the lodestone. So I will show a small piece of lodestone. Here is a small piece of lodestone, right? This possesses weak magnetism. See, here is a small clip. So it clings. Can you observe? Also, end portions of the tags. Can you observe? I think end portions of the tags clings towards the lodestone. So similarly, if you put some more clips, it gets attached. I think all of you can observe. So this is a lodestone magnetized very naturally, right? This was deemed to be the beginning of science of magnetism. Some of the words we come across in the study of magnetism is magnet, magnetic north pole, magnetic south pole, magnetic field intensity, magnetic field lines, etc. Right? So parallelly, so at the same time, at different parts of the world, so many other experiments were going on. The another strange observation made by Greeks was, so when a glass rod rubbed with silk, here is a glass rod. So when it is rubbed with silk, it is used to pick up small bits of paper. Similarly, when a ebonite rod, here is a ebonite rod. So when it is rubbed with animal fur, it is also used to pick up small bits of paper. So something related to the static electricity, right? So this was deemed to be the beginning of science of electricity, right? Some of the words we come across in the study of science of electricity is electric charge, electric potential, electric field, charge distribution, galvanometer, voltmeter, ammeter, etc. These are all some of the important words, jargons, what we come across in the study of electricity. So these two were the strange observations made by the Greeks. These two fields, science of electricity and science of magnetism, both developed independently for many centuries. For so many centuries. So many scientists all around the world contributed for their development. They found many new laws which governs to determine many physical quantities, etc. Of those magnetic field or electric charges, etc. Until 1820. At 1820, one of the scientists called Oersted found a connection between science of electricity and science of magnetism. He was preparing a lecture for his student. He thought that concepts could be better conveyed if it is shown through an experiment, right? No, what he was done was, see here, when he passed current through, imagine this is a conductor, a wire. When he passed current through a conductor, a magnetic compass needle kept nearby got deflected. So can you observe, this is a compass needle. See, I'll show. Here is a compass needle. So small, see this red portion indicates north pole of the compass needle. So when it is suspended freely, this always aligns in the direction of north and south direction. You can see the oscillations of the this magnetic compass needle. Now, what was the Oersted experiment is, imagine this pen is a conductor, right? When he passed current through a conductor, the magnetic compass needle kept nearby got deflected. See, passing current through a conductor is related to the science of electricity. Deflection of magnetic compass needle is related to the science of magnetism, right? So what is happening is, when he passes current through a conductor, this produces magnetic field. This magnetic field interacts with the magnetic field of the compass needle. That's why compass needle got deflected, right? Now there onwards, these two sciences were combined. A single science of electromagnetism was developed. So many scientists all around the world developed this science of electromagnetism. One of the gifted scientists was Michael Faraday. He is so genius that his collected book of lab manual does not contain even a single mathematical equation, right? So he is a very gifted scientist, contributed for science of electromagnetism. Now, he conducted many experiments. There are two famous experiments. One is the magnet coil experiment, other is the coil experiment. Now, let us see the magnet coil experiment. So, all of you know, here is an instrument, what we call as a galvanometer. All of you know, right? Here is a galvanometer which detects presence of current in a circuit. You can see a pointer which shows which is which is positioned at 0, right? So needle is at equilibrium position. So if the needle deflects, it shows the presence of current in a circuit. Also, it shows the direction of motion of the current. So here is a coil. Here is a coil. Look here. So copper coil wound of many turns. Two ends of the coil is drawn as the two ends of the wire here. See here, I think, see here. Here is a coil. Two ends of the coil is soldered to get two free ends here, right? Now, let us connect. I think, let us connect this to the two ends of the galvanometer. See, I am connecting here, right? I am connecting the two ends of the wire to the galvanometer. Now, see, pointer in the galvanometer still does not show any deflection. Here is a coil. Two ends of the coil is connected to the galvanometer. We would not expect needle of the galvanometer to show any deflection because there is no battery connected in the circuit, right? Now, when we move a magnet towards the coil, a curious thing happens. So what is that? So when you move, I think you can observe here. See here. Here is a magnet. Here is a magnet. Can you observe? So I am moving magnet towards the coil. Can you see small deflection in the galvanometer? Small deflection. I think you can observe the deflection in the galvanometer, right? So here what I am doing is just I am moving magnet. I am moving magnet towards the coil. Here is a magnet. Now, so which indicates a current is generated in the circuit. See here, I am moving, current is generated. Now, we have to observe few things here. So slow, when we move very slowly, it produces low magnitude of deflection. Can you see deflection? So if the magnet is withdrawn, it is moved in the opposite direction. The deflection, the momentary deflection is in the opposite direction. If the magnet is stationary with respect to the coil, no matter however, whatever it is closer to the coil, there is no deflection. So current is generated only when the magnet is motion. Faster you move the magnet, the magnitude of deflection is more. Look here, can you observe? I am moving very fastly. See, it shows full magnitude of deflection. It moves beyond 30, right? Can you observe? I think you can observe here, right? So faster you move the magnet, the magnitude of deflection is more, right? So the same thing happens, but exactly in the opposite direction. If we reverse the poles of the magnet, north pole and south pole, if we reverse it, same deflection happens, but in the opposite direction. So why current is generated although the battery is not connected in the circuit is, see here. Here is a magnet, right? The region around the magnet where another magnet experiences a force is called magnetic field. I can sense some sort of force which is repelling here. So the same feeling we can observe if you hold two magnets at your hand, right? So the region around a magnet where another magnet experiences a force is called magnetic field. One cannot see the magnetic field, but one way to visualize the magnetic field is magnetic field lines, which always comes out, emanates from the north pole and gets into the south pole, right? These magnetic field lines are crowded near the poles and spread out when we move apart. So here is a cross-sectional picture. You can see here, small portion. Actually, magnetic field lines forms the loop. This is a small portion. See here. So near the north pole, the magnetic field lines are very crowded. When you move apart, the field lines are wider. So only few field lines are passing through the same given area of cross section here, right? Now, so here is a magnet. Imagine here is similarly here is a magnet. Now, magnetic field lines are very crowded near the poles and spread out when you move farther away. Now, when you move the coil from farther distance to the nearer distance, I think you can see the magnetic field lines. So when you keep the coil somewhere, the coil is completely immersed, bathed in the magnetic field lines of the magnet. Magnetic field lines are hitting the coil. When we move the coil towards the magnet, what happens? The magnetic field lines which are penetrating, which are hitting the coil increases. See, it increases. Okay. When you move the coil from nearer distance to the farther distance, the magnetic field lines linked with which are hitting the coil, penetrating the coil, decreases. According to Faraday, whenever magnetic field lines linked with the coil, which are contact with the coil changes, an EMF is induced, right? This is called induced EMF. If the circuit is closed, a current is induced. This is called induced current, right? So faster, if the rate of change is faster, we move, the change is faster, the magnitude of EMF is more, right? So this is given by Faraday's E is equal to d phi by dt. This is from the expression. So magnitude of EMF is given by E is equal to d phi by dt. So with the lens law, the direction of induced current is given by the negative sign here. So this is the contribution from Michael Faraday. Now, when Faraday made first made public of his remarkable discovery, he was asked, what is the use of it? Okay. So all he was done was a little oddity that a tiny current was produced, very tiny current was produced when he moved a magnet towards the coil. Of what possible use it could be? A tiny current, what possible use it could be? Michael Faraday's answer was, what is the use of newborn baby, right? Physics supplies only the principles, okay? The basic principles that apply no matter what. Today, we see the endless applications of Faraday's laws of induction, betatron. So a particle accelerating machine, which accelerates the electron to very high energies, right? So the betatron works on the principle of Faraday's laws of induction. So the electric generators, electric motors also works on the principle of the Faraday's laws of induction. See here, the electric generators, AC generators. So all these works on the principle of Faraday's laws of induction. The induction cooking utensils, all these works on the principles of Faraday's laws of induction, right? So the little baby grown into a prodigy that has changed the face of the earth in a ways its proud father could never have imagined. So that is the importance of Faraday's laws of induction. Later, in the mid of 19th century, one of the scientists called James Clerk Maxwell consolidated all the ideas of Faraday. Okay, he put forward electromagnetism on sound theoretical basis. There are four equations, what we call as a Maxwell's equation. Maxwell did not discover this equation. So these equations were derived by many scientists like Gauss, Michael Faraday, Ampere. So he worked on those equations. He added corrections to some of the equations. So he picked up four equations and said, these four equations explains electromagnetism completely. So these four equations are called Maxwell's equations, right? What are the importance of these Maxwell's equations? These Maxwell's equations account for the fact that when you turn the ignition key, the car starts. Can be explained on the Maxwell's equation. These are the basis for working of television transmitters and receivers, right? Now, here is a, I will show. Here is a light. Here is a laser light. Can say, I think you can observe. Here is a laser light, right? The medium through which light propagates is called optical medium. Light propagates through water, right? So you can observe, light propagates through water. Water is an optical medium. Light propagates to this transparent plastic. It is an optical medium. Light propagates through glass. Glass is optical medium. But at my back, so light does not propagates through a wall or a board. This wall or board is not an optical medium, right? When a light travels from one optical medium, air is an optical medium. So when a light travels from one optical medium to the other optical medium, light bends, changes the direction. We call it as a refraction. So why this light bends can be explained on the Maxwell's equation. Today, these Maxwell's equations are used all around the world to solve many engineering problems now. So let us study what are those Maxwell's equations. So the first Maxwell's equation is divergence of electric field is rho by epsilon naught. So look here, you can observe Maxwell's equation. Electric field has a positive divergence, which means what? What do you mean by divergence? Divergence means here, here. So here I have two types of lights. One is the torch light, other is a laser light. Can you observe laser light? Compared to divergence means something spreading out, right? So compared to torchlight, laser light has a less divergence. If there is a point charge, the electric field always spreads out, right? So that is the meaning of divergence of electric field. If there is a charge, rho represents the charge density, epsilon naught is the permeability of free space. So the divergence of electric field has a positive divergence if the rho charge is positive, right? Now it has electric field as a positive divergence. This is nothing but Gauss law. Second one is related to the divergence, this del dot. So you can observe del dot. Divergence of magnetic field is 0. So magnetic, you know that magnetic field lines always forms the loops. It forms the closed loops, right? There are no magnetic monopoles. There are no something like we have a independent, a single charge. We cannot have a magnetic charges. That's why divergence of magnetic field is always 0. So now the third equation is nothing but Faraday's law. Curl of electric field is equal to minus dou B divided by dou T. Time varying magnetic fields creates electric field. What do you mean by curl? Curl means something swirling round, right? So imagine, see, I'll show here is a you can see a bottle which comprises of water. Here is another bottle. If I pour the water from one bottle to another bottle, there is no curl. Curl is 0. So instead of this one, see, I am swirling, right? See here, when the water enters the other bottle, it has some rotational effect. Rotational effect means it has some positive value of the curl. Curl means something rotating. It has a swirling effect. So here, so curl of magnetic, the electric field is created by varying the magnetic field with time. So this is the third one. Third Maxwell's equation is nothing but the Faraday's laws of induction. The fourth one is curl B. So here, if we cover this one, curl B, magnetic fields is created by conduction currents. But the second term is nothing but the displacement current. This is the correction, the second term, mu naught epsilon naught dou E by dou T. This is the correction added by Maxwell's to the amperes. It went off. Where is that? Coming. Please. So here, this is the, can you hear? Okay, nice. Thank you. So this is the second term, mu naught epsilon naught. This is the correction added by Maxwell for the amperes law. So magnetic fields are created by conduction currents, as well as the second term is representation of the displacement currents. So time varying electric fields also create magnetic field. So current through a conductor also creates magnetic field. So we have a set of 4 equations, Maxwell's equations. So these Maxwell's equation explains electromagnetism completely. These Maxwell's equations. So basically they are partial differential equations. These are all vector in nature, right? Now we will see some of the properties of electromagnetic waves. In vacuum, these electric field and magnetic fields are propagated in the form of waves. One can derive this equation. So del square E minus mu naught epsilon naught dou square E by dou T square is equal to 0, right? This is electromagnetic wave equation. Similar wave equation one can derive for the magnetic field, del square B minus mu naught, epsilon naught. Mu naught is the permeability of free space, epsilon naught permittivity of free space. So these electric fields and magnetic fields, what are fields basically? Fields are basically physical quantities, so which takes different values at different places, positions, right? So electric field and magnetic field are basically the vector fields, right? These electric field and magnetic fields propagate as a wave. When we compare these two equations with the standard equation, wave equation, del square psi minus 1 by v square, dou square psi by dou t square is equal to 0. We can compare this. This is similar. So we can equate velocity. The velocity of the disturbance happens to be 1 by root of mu naught and epsilon naught. The value happens to be 3 into 10 to the power of 8 meter per second. Now, at the same time, parallelly, many experiments were going on all around the world to determine speed of light, like Michelson experiment, Morley experiment, etc. From Jamison interferometer, etc. So the velocity of light happens to be 3 into 10 to the power of 8 meter per second. So Maxwell's determined the speed of electromagnetic wave is also 3 into 10 to the power of 8 meter per second, right? The speed of light is also 3 into 10 to the power of 8 meter per second. So he came to a conclusion that light is also a electromagnetic wave, right? So he unified the areas of electromagnetism and optics. So optics is not a different one. It is a serious part of electrodynamics, electromagnetism. Now, how do you produce these electromagnetic waves? Now, we have some, see, we have studied the oscillations of a pendulum. Now, here is a small bob connected to a thread. Other end of the thread is connected to a rigid support, right? If you pull the bob aside, release the bob, it moves back and forth. We call it as an oscillation. We have an expression for time period, everything, right? This is an oscillating system. This can be represented by graph also, right? Similarly, if you imagine this is a charge, right? A stationary charge produces electric field. If this charge is not moving in any direction, so stationary charge produces electric field at a point. So if the charge starts to move, the electric field at this point changes because the distance also changes. So when it is nearer, the electric field is more. When it is farther away, the electric field is less. Imagine at this point we are going to measure a electric field with help of some instrument. If the charge keeps on oscillating, what happens? If it is charged, move back and forth periodically, what happens? The electric field at this point changes, right? This time varying electric field produces time varying magnetic field, right? This time varying magnetic field in turn produces time varying electric field in a mutually perpendicular direction. Again, that time varying magnetic field produces electric field produces magnetic field, and it keeps on moving. The disturbance progresses, passes. If the charge stops its oscillation, once it set into oscillation, it produces electromagnetic wave. Once it stops oscillation, the wave keeps on going. It's a source free, right? Now, so the electromagnetic waves are produced by oscillating charges. Imagine we are receiving light from a star which is about 4.2 light years away. So which is Proxima Centauri, let's say, right? At this moment, let's say the star sends last light, a signal. Now it explodes, right? Now the last signal, we receive the signal for further 4.2 light years, right? So further light years, although the source stopped sending these electromagnetic waves, so that information reaches only after 4.2 light years. So these electromagnetic waves, the disturbance is created very fast at the speed of 3 lakhs kilometer per second, 3 into 10 to the power of 8 meters per second. Now, so energy. So one of the right. One of the we'll study something about energy of a electromagnetic wave, right? So in physics we study many laws, many. Okay. In physics we study many laws. One of the important law is law of conservation of energy. This energy has different forms, right? We have light energy, electrical energy, etc. Please switch on. No. Right. Look here. I have a bulb. Bulb here. Bulb is glowing. I have a circuit here. I think you cannot see the. Clap. Here is a clapping circuit. Clap. Clap. See, once we clap, the bulb glows. Clap. Once again, clap. Bulb lights up. This is a clapping circuit. See here what is happening is, how come bulb knows we are clapping? Here is a inside, here is a circuit. You cannot see, here is a circuit. Here is a small sensor inside the circuit. Small microphone inside the circuit, which picks up the sound energy and converts into a small electrical signal. These electrical signals are amplified by further stages of transistor, right? Then, so here in this process, sound energy is converted into electrical energy. Like that, we have a lot of different forms of energy: sound energy, light energy, mass energy, potential energy, kinetic energy, etc. These electromagnetic waves also carries the energy. In an electromagnetic wave, the energy is contained in electric field as well as a magnetic field. Now, what is the energy contained in an electric field? The energy contained in the electric field is given by half into epsilon naught into E square. This is the energy stored in an electric field, right? So similarly, the energy stored in a magnetic field is given by half into B square. This is divided by mu naught. As usual, epsilon naught, mu naught. Epsilon naught represents the permittivity of free space. Mu naught represents permeability of free space. So energy is carried by both electric field and magnetic field. What is the total energy? Total energy is the combination of contribution from electric field and magnetic field. Can be written like this: half into epsilon naught into E square plus half into B square divided by mu naught. This is the total energy contained. This energy is equally shared. This energy is equally shared between electric field and magnetic field. We define a quantity what we call as the Poynting vector. The energy density, that is energy transported per unit area per unit time, is given by the Poynting vector. Here is a Poynting vector. So S is called Poynting vector, free space 1 by mu naught into vector E. Here is a vector E cross vector B. Here is a Poynting vector. What is this Poynting vector? Imagine a beam of sunlight is coming. A beam of sunlight is coming. Hold an area of cross section. Here is. So let the length of the area, length is about 1 meter, breadth is about 1 meter. Let's say a beam of light is coming like this. So length is about 1 meter, breadth is about 1 meter. So the light passes through, just like the light, just like here. The light passes through this area of cross section. This is unit area of cross section. Some amount of energy is transported. It is transported. The energy transported in 1 second. The energy transported in 1 second is given by the pointing vector. So as I show the formula, so 1 by mu naught into so E cross H, right? So some of the other properties of electromagnetic waves are, so electromagnetic waves carries the momentum. So these electromagnetic waves exhibit radiation pressure. So the sun rays exhibit radiation pressure of about 7 into 10 to the power of minus 6 Newton per meter square. Now, so these electromagnetic waves are transverse in nature. So one can derive the transverse nature of the electromagnetic waves from Maxwell's equations. So till now we have discussed, these are all some fundamentals and basic ideas related to the science of electromagnetism. Let us summarize a bit. So we started our journey from physics. So physics is a study of nature. So with the help of scientific method, we acquired so much of knowledge, right? Observation, reason, and experiment, we call it as a scientific method. So many scientists contributed to the advancement of science, but long back, these Greek people got curious about two strange things. One is related to the science of magnetism, other is related to the science of electricity. So these two sciences, science of electricity and science of magnetism, developed by so many workers, so at all around the world, independently for many centuries till 1820. So some of the words we come across in the study of electricity is different, like ammeter, voltmeter, galvanometer, etc. The words we come across in the study of magnetism is quite different: magnetic north pole, magnetic south pole, etc. These two sciences were combined. So there is a connection between these two sciences at 1820 made by Oersted. So when he passed current through a conductor, what happens? The magnetic compass needle got deflected. So there is a connection between science of electricity and science of magnetism. So many people contributed. One of the gifted was Faraday. We have seen the magnet and coil experiment. We have observed the movement of needle in the galvanometer when we moved a magnet towards the coil. Also later, so James Clerk Maxwell consolidated all the ideas, and all electromagnetism is put forward on a sound theoretical basis. There are four Maxwell's equations, basically partial differential equations. It uses vector fields like electric field and magnetic fields, right? So these four Maxwell's equations explains all sorts of electromagnetic and optical phenomena, right? So we have seen some of the properties related to the science of these electromagnetic waves. So light is optics is only a part of the electromagnetic spectrum. All of you have seen, right? So madam, thank you very much. Please.
On behalf of all of us and Vidyodhaka College of Engineering, I thank Dr. Mahadeva Prasad for giving a beautiful explanation on the fundamentals of electromagnetism. We learnt the fundamental basics of electromagnetism with such a lovely demo sessions. I thank sir for this. Thank you very much, sir.